Look at this landscape. It is rugged, porous, and seemingly chaotic, but hovering right above it are the Navier-Stokes and Bernoulli equations, the strict mathematical laws of fluid dynamics. Bridging the gap between that raw terrain and these precise formulas is where the science of hydrology actually begins. In hydric engineering, water is a dynamic structural constraint rather than a static commodity. This articulating axis defines the hard physical limits of a region's social, economic, and environmental development. But before we can design the infrastructure to control that axis, we face a massive calculation problem. We have to map and measure a highly volatile fluid as it moves across hundreds of square miles of fractured rock and soil. To solve this, engineers use a macro accounting framework known as the water balance, or balance hídrico. The water balance applies the foundational physics law of the conservation of mass across a sprawling geographic scale. This chart shows the international standard for the calculation, defined by the World Meteorological Organization. It breaks down into the equation delta S equals I minus O. The premise is absolute. Over a fixed time interval, total mass entering an area must equal the mass leaving, plus the net volume remaining stored behind. Grounding that abstract physics into a workable geographic model is mandatory. It is the only way to convert unpredictable natural flows into secure, reliable civil infrastructure. To make the mass conservation model work, we need a closed physical boundary, the geographic basin. We establish an initial state, freezing time to index the absolute volume of water held inside. The most visible variable is active surface storage, water circulating through riverbeds and canals. Next, we map static storage, massive reserves pooling in natural lakes and reservoirs. Then we look for transitional zones, calculating liquid mass trapped within swamps and wetlands. Pushing deeper, a critical volume is retained as soil moisture, locked within porous ground strata. Finally, we measure the biological vector, calculating the sheer weight of water absorbed inside the living tissue of the region's plant and animal life. We aggregate these 5 distinct metrics. This sum gives us the total baseline storage variable for our target basin. If an engineer underestimates any of these hidden storage vectors, the calculation breaks. The resulting infrastructure will buckle under a load it wasn't designed to carry. With storage indexed, the model pivots to track the inputs. The primary entry points are atmospheric. We measure both liquid precipitation falling as rain and solid mass depositing as snow and hail on the peaks. We also track the hidden subterranean inputs, groundwater continually seeping into our system horizontally from adjacent, higher elevation basins. But the most difficult input to model isn't atmospheric or geological, it is engineered. We call this a trasvase, or an interbasin transfer. It is a massive artificial injection of water driven by human intervention. Take 2 parallel valleys separated by a mountain range. To maximize power generation, engineers bore a massive tunnel straight through the bedrock to connect them. This diverts hydric flow from the neighboring basin, consolidating physical mass to drive the turbines of a centralized, high-yield hydroelectric plant. Modern hydric management cannot rely on natural topography alone. The model has to account for these massive clumbing networks that actively overwrite regional inputs. To finish the conservation equation, we map the final component, the outputs leaving the system. We measure natural atmospheric losses. This includes water evaporating off the soil and the constant transpiration driven by biological tissue. We track surface flow, rivers actively draining natural runoff past the lowest boundary of our basin and out to the ocean. And we log the engineered outputs, the massive volumes mechanically pumped out every day for urban sanitation, heavy industry, and agricultural irrigation. With all variables captured, the World Meteorological Organization framework locks together. We mathematically balance the mapped inputs against the mapped outputs to find the exact net change in basin storage. This finalized balance is the non-negotiable mathematical baseline. It has to be perfectly solved before a single cubic meter of concrete is poured. This photograph of the Galeito Ciego Dam illustrates exactly how these equations translate into physical concrete anchored into bedrock. Look at the massive spillways. Megastructures like this are specifically constructed to manipulate the storage variable of the water balance equation. Operating them requires constant tension. engineers release a steady output to sustain the population downstream, while keeping enough empty capacity behind the wall to absorb highly volatile, extreme storm inputs. When a massive storm hits, the equation requires an immediate response. The structure is forced to execute a high-pressure release just to maintain its integrity. In this image of Galito Ciego discharging, you see pure kinetic energy. Mathematically, it's an engineered output dictated by the basin's strict storage capacity. This dynamic is exactly why organizations like UNESCO maintain a strict mandate on hydric resource management. Their directive requires that the water balance model be used to quantify available resources, while simultaneously measuring the exact impact human extraction has on the local cycle. Because water remains the central articulating axis, if the mass conservation calculations fail, the power grid fails, the agriculture dries up, and the regional economy stalls. Absolute mastery of the water balance elevates the civil engineer to an architect of sustainable ecosystems.